Hello and welcome to our deep dive. Today we're looking at a topic from Unit 5, coordination compounds, and it's one that often causes confusion. We are going to crack the concept of isomerism.
It's good to be here. And you're absolutely right. This is one of those topics that can be the difference between getting full marks and, losing a lot of marks in the board exams.
Exactly. So before we get into any definitions, I want to start with a puzzle. Picture this. You're in the chemistry lab and you're holding two test tubes.
Okay.
You look at the label on the first one. It says CoNaOR, ClBr. Then you check the second test tube and the label is exactly the same, CoNaO, ClBr.
Right. So same formula, 1 cobalt, 4 ammonia ligands, 1 chloride, and 1 bromide.
Yes. So my brain immediately thinks they are the same substance.
Yeah.
They have to be. But when you hold them up to the light, one liquid is a sort of blue-green and the other is purple-red.
A very, very different appearance.
So my question is, and I'm sure every student listening is thinking this, how is that possible? Is the label wrong? Did someone just mess up the experiment?
No, not at all. The labels are completely correct. The ingredients are identical. But you're looking at two completely different compounds.
That feels counterintuitive.
Yeah.
How can they be different compounds with the same formula?
Well, that's what today is all about. This isn't just about memorizing some definitions. It's really about understanding geometry, about understanding 3D space.
And for our Class 12 listeners, why is this so critical to understand?
It's crucial because isomerism explains why something like CoNH can exist as two different substances with different properties. And in the real world, this matters a lot. Think about pharmaceuticals. One version of a drug formula might cure you, while the other, the isomer, does absolutely nothing, or worse.
And I'm guessing for exam, this is a pretty common area for questions.
Oh, definitely. You'll often see 3 to 5 mark questions that ask you to draw these different structures or explain the difference, so it's an important area.
Okay, that definitely raises the stakes. So let's start from scratch. At the simplest level, what are isomers?
Okay, at the simplest level, isomers are compounds that have the exact same molecular formula but different arrangements of atoms.
Same formula, different arrangement. Okay.
Yeah.
Let's try an analogy to make arrangement a bit more concrete.
Sure. Let's imagine. Think of a room with 6 fixed spots for furniture. That's our central metal with its 6 coordination sites.
Okay, 6 spots in a room. Got it.
And the formula, let's say, is 4 red chairs and 2 blue chairs. Those are your ligands.
4 red, 2 blue.
Now, you could arrange them by putting the 2 blue chairs right next to each other, together in a corner.
Mm-hmm.
Or you could put 1 blue chair at the front of the room and the other one at the very back, as far apart as possible.
But the total count is still 4 red chairs and 2 blue chairs.
Exactly. The inventory of furniture is the same, but the layout is completely different. That's isomerism. Same formula, different structure.
Right. So this brings up a common confusion that I know I had. Does the order you write the formula on paper matter? Like, does writing Cl before Bre make it a different isomer?
That is a classic misunderstanding, and it's so important we fix this right now.
Okay.
Writing CoNH-ElBr versus, say, CoNH-ElBrNH, it means absolutely nothing. They are the same compound.
So the paper order is irrelevant.
Completely. Isomerism is about the actual 3D geometry, the real-world arrangement in space, not about the order of ink on a page.
Okay, that's a very important clarification. Paper order doesn't matter. 3D geometry is everything. So let's get into that geometry. You hear these terms cis and trans all the time.
Yes, that's geometric isomerism. It's the most common type you'll encounter.
So what do cis and trans actually mean?
Let's use another analogy. Let's call it the greeting circle. Imagine 6 people standing in a circle representing an octahedral complex.
Okay, 6 people in a circle.
And let's say 2 of these people are type A and the other 4 are type B. Maybe the 2 type A people are the 2 glue chairs from our last analogy.
Or 2 A's and 4 B's.
Okay, in one arrangement, the 2 type A people are standing right next to each other. They're neighbors. They can easily have a conversation.
They're adjacent.
Yes. When the same groups are adjacent or next to each other, we call that the cis arrangement.
Cis for adjacent. Got it.
Huh.
So what's the other way?
The other arrangement is when the 2 type A people stand directly opposite each other across the circle, as far apart as they can get.
Okay, so they're on opposite sides.
Exactly. And when they are opposite, we call that the trans arrangement.
So cis is neighbors, trans is opposites. Simple as that.
Simple as that. Same people in the circle, just a different spatial relationship. And this simple difference explains why you saw a blue-green liquid and a purple-red one.
Wow.
Yeah.
How does just moving 2 atoms from being neighbors to opposites change the colors so drastically?
Well, it's because that arrangement changes the electric field around the central metal ion.
Yeah.
And that change in the field affects how the metal's d electrons absorb light.
Okay.
So a cis arrangement creates one kind of field, so it absorbs, say, yellow light, and you see the complementary color, purple. The trans arrangement creates a different field, absorbs a different color of light, and so you see a different color.
That's fascinating. So the geometry directly impacts the physics of light absorption.
Precisely.
Now, you mentioned earlier this could be a matter of life and death. I'm assuming you're talking about the famous example, cisplatin.
Yes, exactly. This is the most important application to remember. Cisplatin is an anti-cancer drug. The formula is PT-NAvis.
And it has a trans version, transplatin.
It does, same
Yeah.
formula. But it's completely inactive as a cancer drug.
Why? What's the difference?
It's all about the shape. The cisplatin molecule, because its two chlorine atoms are next to each other, has the perfect shape to clamp onto the DNA of a cancer cell. It creates a kink in the DNA and stops the cell from replicating.
So it's like a specific key fitting into a lock.
A perfect analogy. But transplatin, where the chlorines are on opposite sides, is the wrong shape. It's too wide. It can't bind to the DNA in the same effective way, so it just doesn't work.
Incredible. So the geometry, the cis shape, is literally what makes it a life-saving medicine.
Yes. It shows that same formula does not mean same medicine.
Right. Okay, so that's geometric isomerism. But there's another whole category, isn't there? Structural isomerism.
Yes, and this is where you have to be careful with the definitions for your exam. There are a few types, but let's focus on the main three: linkage, ionization, and coordination.
Okay, let's take them one by one. First, linkage isomerism.
Linkage isomerism happens when you have a special kind of ligand called an ambidentate ligand.
Ambidentate. Sounds like ambidextrous.
It's the exact same idea. Think of a ligand like the nitrite ion, NOU. It has both a nitrogen atom and oxygen atoms. It can sort of shake hands with the central metal using either atom.
So it can attach via the nitrogen, or it can flip around and attach via one of the oxygens.
Correct. If it attaches with its nitrogen atom, we get one compound. If it attaches with its oxygen atom, we get a completely different compound, a different isomer.
And does this cause a visible change too?
Absolutely. The nitro complex, where it's bonded through nitrogen, is typically yellow, but the mitrito complex bonded through oxygen is red. Just flipping the attachment point changes the color.
Wow. Okay, so linkage isomerism is all about which atom of the ligand connects to the metal.
You've got it.
Next up, ionization isomerism. This one sounds a bit more complex.
It's actually quite simple if you think of it like this. Imagine the coordination complex is a VIP room at a party.
Okay, I like that.
The part inside the square brackets is the VIP section. The ions inside are exclusive. The ion outside the bracket is in the general area.
Right, inside is VIP, outside is general admission.
Now, let's say you have a compound where a sulfate ion is inside the VIP section and a bromide ion is wandering around outside.
Okay, sulfate inside, bromide outside.
When you put this in water, only the bromide outside is free to react. The sulfate is trapped inside. But now, imagine it's isomer. We swap them. The bromide goes inside the VIP section, and the sulfate is kicked outside.
So it's the same guest list, just who is in the VIP room has changed.
Exactly. But now the sulfate is free to react in the solution. So if you do a chemical test for sulfate ions, the first compound will show no reaction, but the second one will react immediately.
Ah, so they have the same formula, but give different results in chemical tests.
And that's how we know they are different compounds. That's ionization isomerism. A swap between an ion inside the sphere and one outside.
That's a great way to remember it. Okay, last one. Coordination isomerism.
This one is the easiest to spot on paper. It happens when your compound is made of both a complex soncation and a complex anion.
You mean two sets of square brackets in the formula?
Yes. If you see two square brackets, you should immediately think of coordination isomerism. Imagine you have one metal, say cobalt, with ammonia ligands, and another metal, chromium, with cyanide ligands.
Okay, two separate complexes together.
Coordination isomerism is simply when they swap ligands. The ammonia ligands might move from the cobalt to the chromium, and the cyanides move from chromium to cobalt.
So they just trade partners.
They trade partners. That's all it is. So if you see
Yeah.
two brackets, it's a partner swap. It's coordination isomerism.
Fantastic. So now let's switch to exam mode. I, as a student, I see a question on isomerism. What are the key clarity lines I need to remember?
Okay, exam safe lines. Number 1. Geometric isomerism, the cis-trans type, can't happen if all the ligands are the same. You need at least two different types of ligand for it to be possible.
Right. If everyone is identical, there's no neighbor versus opposite.
Correct. Number 2, don't forget the structural types. Remember the triggers. Ligand like NO, think linkage. Ion, outside the bracket. Think ionization, 2 brackets. Think coordination.
That checklist is super helpful. What else?
A very important point about stability. Remember, these isomers are distinct, stable compounds. They don't just flip back and forth at room temperature. The green one stays green, the red one stays red.
Okay, they're not in equilibrium, they are separate substances.
Yes. And finally, isomers have different physical properties like color, solubility, melting point. That's how we can actually separate them in a lab.
Perfect. That's all very clear. So let's do a super quick summary to wrap this all up.
Let's do it.
Okay, so first, the core idea. Isomers have the same formula, but a different arrangement of atoms.
Exactly. Same ingredients, different layout.
Second, the main analogy to remember is the greeting circle. Neighbors are cis, people on opposite ends are trans.
And that simple difference is what makes cisplatin a cancer drug while transplantin is useless.
And finally, geometry defines the compound. It's not just about the list of ingredients you start with.
That's the most important takeaway. The structure is everything.
Brilliant. Now, before we sign off, I want to give you, the listener, a quick task to really lock this in.
Good idea.
Grab a pen and paper right now. Seriously, pause and do it. Draw the complex coral first. Draw the cis isomer. Put the 2 chlorine atoms next to each other. Then draw the trans isomer. Put the 2 chlorines on opposite sides.
The moment you draw it with your own hand, the concept will stick. You won't forget it.
Exactly. Because it's not just lines on a page. It's the difference between green crystals and red crystals. It's the difference between a medicine that works and one that doesn't.
Well said.
Thank you so much for this deep dive. We really hope this helps you all crack this topic.
All the best with your studies. Happy learning.